All right, so welcome to lesson 1 of distance learning. We're going to go over 4.3 today, and we're going to start by reviewing what it means to be a linearly independent set, and then we're going to use that definition to prove something very specific. We're going to, just like last time when we were looking at the null space and the column space, for 4.3, once we prove that something is linearly independent, we're going to try to use that as something called a basis for a whole either dimension or a whole subspace. And we'll get to what that means in a few minutes. But first, just kind of a review from chapter 1 is what makes a set linearly independent. So in order for it to be, let me try to refocus this. There we go. In order for it to be linearly independent, we're really trying to solve the equation where we add up all the vectors and get the zero vector. In order for vectors to be linearly independent, it means the only way for us to add up all of those vectors, all of the vectors in the set, and get the zero vector is if we use constants that are all zero. Okay, that means that none of the other vectors, v1 through vp, are a linear combination of some other set. And so if it's linearly dependent, then you can either write it in the same way, where we're setting this entire equation equal to 0, or you could move some of these vectors to the other side. So you could say if there exists weights or constants that are not all 0, such that when you add up all the vectors, you can get the zero vector. Another way to say this is, again, right here, if ax equals 0 has only the trivial solution, and here if the vectors are linearly dependent, ax equals 0 has a non-trivial solution. So, other things that are more review. A set that contains the zero vector is automatically linearly dependent. This is going to happen a lot, so I'm really sorry for PJ. It's linearly dependent. And a set of two vectors is linearly dependent if the other one is a multiple of the other. So here, in this is a set of vectors. Now that we're considering an object, it could be a matrix, could be a polynomial, could be something else, to be a quote-unquote vector. Here, this set is linearly dependent because it contains the zero vector. And I'm going to write vector in quotes. Okay, so the zero matrix. Here, are these two linearly dependent or independent? Well, I'm noticing that if I multiply a11 by 3, I could get b11. Same thing for a12 and b12, so on and so forth, except not the last component. I could not multiply 4 by 3 and get 10. So this is a linearly independent set because there is no c, so that c times 1, 2, 3, 4 would be equal to 3, 6, 9, 10. Okay. So they're not constant multiples or a scalar multiple of each other. Okay. And to prove that a set is linearly dependent, all we have to do is prove that one of the vectors is a linear combination of the preceding vectors. So let's try this with polynomials. So a new object, let me move this plant that keeps getting in my way. Okay. All right, so just like we were considering matrices up here, vectors, quote unquote, we're now going to consider these polynomials each a vector. So we're going to ask, is this set a linearly dependent set? Okay, and you could probably think about that yourself. But if I can make an equation where P3 is the sum of P1 and P2 with some constants, then it's linearly dependent. So I could say that P3 is actually 4 times P1 plus 2 times P2. And that, if I sub that in just to make sure, P3 is 4 times P1 is T, and P2 is T squared, then yes, okay, P3 is a linear combination of P1 and P2. Therefore, P1, P2, P3 is a linearly dependent set. Not so bad. All right, so proving things are linearly independent or dependent, we can do that pretty easily. We're looking for linear combinations. But what can we use this for? And that is to create a basis. So when we're thinking about, page, a basis, I want you to think about the most basic set of elements or vectors that you would need to span the whole set, to create everything in that range. So here, just visually, I am looking at H being this plane. And let's pretend it extends infinitely. Okay, and we're asking which of the following are valid descriptions of H. So this says that H is a span of V1, which is here, and V2. Okay, and that's true. Those two vectors are linearly independent. I can see that one of them will cover this going this direction, the other one will cover this direction. So I would say that that's a description of H. I could also use V3 though, because V3 and V2 go along the same line. So I could substitute V2 in for V3 and say that this is also a valid description of the plane H. But the span of V1 and V2, that is not H, because that is only a line. This line over here specifically. And last but not least, we could also use D, because technically H is the span of V1, V2, and V3, but this is inefficient. We have too many vectors. We're making a plane. All we need to span a plane is 2 vectors. So if I have more than 2 vectors, this is an inefficient set, okay? Because the set is linearly dependent. Basically, I'm saying that I don't need to use both V2 and V3 because they both describe the same line in the same direction. So I don't need to use both of them to just span all of H. I could use one of them, like I did up here in A and B, but I don't need to use both. They describe the same thing. So a basis is the most efficient spanning set that contains no unnecessary vectors. Therefore, our basis, when we make a basis, we want it to be linearly independent. We don't want there to be any repeats. We don't want there to be any other linear combinations. So if we have H, a subspace. Now, if you need to pause here and go back and look at what a subspace is and what qualifications a subspace needs to be, you can basically, again, think about it being though, here we have a big dimension, pretend it goes on infinitely, and a subspace is some subset of items in here that follows some very specific rules, like the zero vector and vector addition and scalar multiplication. Okay, so if we want to make if this is a subspace, then we can say that an index set of vectors, that just means they're different, they are marked differently. This will count as a basis for H, meaning this is kind of like, I could make anything in H out of this set of vectors. What we called the spanning set for the null space. Okay, so write that down. Spanning set. Then 2 things must be true to create that basis. 1, the basis, the set of vectors, has to be linearly independent. If it's linearly dependent, we're not using the most efficient set. And 2, it must span all of the subspace that we are looking for. Okay? Both of these have to be true in order for this to be a basis. We want to use an efficient set, and we want to cover everything in this space. Okay, that's what those 2 conditions kind of mean. So we want to show that these 3 vectors, this is, again, if you want to think about it in multi, this was I, J, K. So for I, J, K, we want to show that they are a basis for the 3-dimensional space. Okay, and we can actually use the IMT. If we make this into a matrix. So if I put the 3 vectors E1, E2, E3 into a matrix, E1, E2, E3, that looks like 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I'm checking for 2 things. Are they linearly independent? Okay, there's a pivot in every column, and yay, those definitions are not going away. sorry, my handwriting's so bad. Pivot in every column, therefore E1, E2, E3. The vectors are linearly independent. Okay, and 2, there's also a pivot in every row. E1, E2, and E3 span R3. Okay, since both of those things are true, both of these things are true, therefore, this set, E1, E2, E3, form a basis for R3. Okay, not so bad. Now we want to try it with polynomials. Okay, so we want to show that Pn, which is all polynomials up to degree n, not greater than degree n, but up to degree n, kind of like a Taylor polynomial. Okay, we want to show that this set, the set of each kind of individual item of each next degree, is a basis for all polynomials of degree n. So I'm actually going to do something, we're going to do some creative and critical thinking here, so you can check that off your box for today. So we're going to let there be a matrix that looks like the identity matrix, but along the diagonal, we're going to put all of these elements. Okay, so we'll go all the way down, and it goes all the way across. And on the diagonal, I've got t squared, and then it goes all the way down to t to the n. Okay? So it's a diagonal matrix with the elements of this set along the diagonal. Okay? So again, thinking about this like we did up here, this matrix has a pivot, technically a weird looking pivot, but a pivot nonetheless, in every row and column. Okay? And which means columns of A, each of these elements are linearly independent and span all polynomials of up to degree n. Therefore, S is a basis for Pn. Okay? And there's a little note in the field notes, so if you want to pause here and look at that, about how we would multiply A times a vector full of constants, and that would add up together to make a polynomial of at most degree n. You can pause and look now. But you can see how us putting things in matrices and either row reducing or just kind of looking, making observations about what's there right now is still helpful for determining things later. So let's go ahead and look at other vectors that may still be, even if they're not kind of our unit vectors or our most basic elements, they could still form a basis. Because remember, our basis only needs to be two things. We only need to have it be linearly independent and span all of the subspace or the dimension that we're looking for. So if I look at example 6, I see that I have 3 vectors, and we're asking, is this still a basis for R3? Okay, so if you want to pause here and go ahead and try this yourself, now is a great time. But if you still need a little bit more help, what I'm going to do is I'm going to put these vectors in a matrix. Okay, because putting them in a matrix will tell me, 1, if I have a pivot in every column, and if I have a pivot in every row. When I row reduce this in my calculator, you could also do it by hand if you want some practice, but I am getting the identity matrix, which means that since there's a pivot in every column and row, V1, V2, and V3 are linearly independent and span R3. Therefore, the set V1, V2, V3, even though they are not kind of the unit elements we would think about in 3 dimensions, are a basis. Excuse me, this is a set, so I should use proper grammar and say that this set is a basis for R3. Okay. All right, and then we'll just talk through these ones, but if you need to pause and write down the explanation, go ahead and look at the field notes. So we're looking for why each of these is not going to be a basis for R3. So if I think about putting these vectors into a matrix, I'm going to realize that I cannot have a pivot in every column. If I have 4 columns and only 3 rows, I can't have a pivot in every column. Therefore, these cannot be a linearly independent set. So this cannot be a basis for R3. And on the opposite side, if I don't have enough columns, I can't have a pivot in every row. Therefore, these 2 vectors by themselves can't span R3 because there's not enough room to have a pivot in every row. So neither of these could form a basis for R3. Okay, now what about what we've been talking about for the last couple days? A basis for the null space. Okay, that means we're looking for linearly independent vectors that will span the null space. So this was actually example 1 from 4.2, excuse me, example 1 from 4.2, okay? And we found that the null space of this matrix A was the span, and you can go back and look if you need to figure out how we did this, of these 3 vectors, negative 1, 2, or excuse me, negative 2, 1, 0, 0, 0, negative 13, 0, 6, 1, 0, and negative 33, 0, positive 15, wow, my writing is horrible, 0, 1. Okay. This was the span. These 3 vectors spanned the null space. So that's actually already qualification number 1 for being a basis, is that the vectors in the basis must span the space you're looking for. And these 3 vectors span the whole null space. Now, are they linearly independent? Yes, we've already verified that, but if you needed to just do some observation, you could look across the row here. There's no way that these 2 vectors could combine to be this 3rd vector here because this 1 is here and they have zeros here. And the same for the 4th row and the 5th row. Okay? None of these vectors could be a linear combination of the other ones. So automatically, what we were doing a couple lessons ago in I think 4.2, okay? Oh wait, this is 4.3. So yes, 4.2. So in 4.2, what we were doing by finding a description of the null space was actually finding a basis for the null space. So this is a basis for the null space of A. Okay. This is kind of really easy. Now, what if we wanted to figure out a basis for just a random set of vectors? Let's say I just give you just a subset. Okay. Then we have something called the spanning set theorem. Basically, and this is nice, it's very simple, if one of the vectors, am I looking? Nope, I'm too far up. Whoop, there we go. If one of the vectors is linearly dependent on the other ones, we remove it, and then we are automatically given a basis for that set of vectors. Notice that I'm just trying to find a basis for these 3 vectors. Basically, and this seems a little bit trivial, but it could be applied if you had some very specific set of data that you needed to make sure you could reach, or some very, like a very specific area geometrically that you wanted to be able to map things to. But if I wanted to find a basis for this set of vectors, I basically use those vectors and make sure they're not linearly dependent. So here, since we can observe that 2 times v1 plus 3 times v2 would be equal to v3, we eliminate. Wow. This is what happens when you don't go to school. Eliminate v3 to make a basis. And this will help us in a second find a basis for the column space of a matrix. So therefore, in this case, v1 and v2 form a basis for the set v1, v2, v3. Okay, basically we got rid of anything that was linearly dependent. Okay, and this is to say that as long as the subset, okay, okay, is not just the 0 vector, okay, as long as this either dimension or subspace or subset is not just the 0 vector, then some subset in there, okay, will still be the basis for H. So we can just use the vectors that are already in H, these vectors already in H, to form a basis for H. So if we want to find a basis for the column space, which means I'm looking for the vectors, only the necessary vectors that would help me create all of the linear combinations of these 4. Do I need to use all of them, or can I use less of them? Okay, so we need to know, are these columns linearly dependent or independent? Okay, does each of them bring something new and unique to the set, or is something a repeat of what we already had, and then we want to eliminate it? Okay, so if we row reduce this matrix A, and you can go ahead and pause and do that in your calculator just to be sure. Okay, but I'm going to get 1, 0, 0, 0, 2, 0, 0, 0. So already I can see that the second column is linearly dependent. Okay, and you could probably see that from observation. It is basically the same thing as the first column. So I don't need the second column to form a basis for the column space of A. I don't need the second column to be able to make a new linear combination of these 4 vectors. I could have just used the first column. Nice. Third row is 0, negative 1. Oops, sorry. 0, 1. I was reading the old one. 0, 1, 0, 0. So that is independent. But then the last column is 4, 5, 0, 0. So that is, again, dependent. Okay, this was a combination of columns 1 and 3. So I don't, again, need column 4. Okay, so x2 and x4 are free. Therefore, they are linear combinations, we'll say combos, of x1, not x1, a1, and by they, let's be more specific. I need to be more mathematical. So a2 and a4 are linear combinations of a1 and a3, because those are my column names. Okay, so we eliminate these 2 vectors in order to make a linearly independent basis. So the vectors 1, 2, 3, 4, and the vector 0, negative 1, 2, 0 form a basis for the column space of A. Okay, and again, even if, here's another fun fact, elementary row operations on a matrix do not affect the linear dependence relations among the columns. Okay, it just shows you which ones are dependent on the other ones. So once you've looked at the row reduced form, you can then go back and determine which of these columns are the linearly dependent ones and eliminate them. Notice though, I used these 2 columns. I had to go back to the original matrix to determine which 2 columns formed a basis for the column space of A, because if I had only used this row reduced column and this row reduced column, I would only be able to create vectors, linear combinations that had entries in the first row and the second row with numbers. Here, by using the original 2 columns, I'm able to create linear combinations that have any entry kind of from top to bottom. You know, well, maybe not any entry because I can't span Rn or R4, but I can create vectors that have a non-zero element in each place at one time. Okay, so let's do one more. Actually, I think you can do this last one yourself. Okay, same example. I want to use these 3 vectors to form a basis for the span of those 3 vectors. So basically, again, I'm figuring out which of these is linearly dependent, if any, and whichever one is linearly dependent, I eliminate it. Okay, and then the ones that are remaining are the ones that form the basis for the span of these 3 vectors. Okay, and I've typed up a quick recap here at the bottom. But that's just kind of that was kind of it for today. We are going to move on next time to what do we use a basis for. But today I kind of just wanted to talk about how do we make a basis, and then why Does it have to be linearly dependent? What does it mean to be linearly independent and dependent? And how do we test that? So if you have questions, please email me or send me a text to remind.